तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we took an example where the FET was biased using a single power supply, and we also had an example in which we had worked out how to operate the FET in a particular operating region, 1 milliampere, 10 volts, etc. IDSS 1 milliampere and VDG equal to 10 volts. Now, the same example we will consider here. The same FET is used. Design a FET NMOS with K equal to 1 milliampere per volt square and Vt equal to 1 volt with dual supplies now, 2 supplies. The supply voltage is not yet fixed. We have to fix it for certain design criteria. Supplies for symmetric output swing. Now, I am treating this in a different manner. I am designing this amplifier for symmetric output swing of 10 volts. I want a symmetric output swing around the quiescent of 10 volts on either side of quiescent voltage. Okay. So, this, if it is having a quiescent voltage of some value, on either side of this there should be a swing of 10 volts at the output around the operating point. The operating point is 1 milliampere. This should be a stable operating point of 1 milliampere. Okay, IDSQ. Evaluate the voltage gain, estimate the coupling and bypass capacitors. This is similar to the bipolar situation for Rs equal to 100 kilo ohms. Now, the amplifier configuration is already known to us. Here the source is directly coupled, because we are using dual supply. So, you can directly couple the source. And there is no DC current that is likely to go through the source, no problem. So, this is the advantage of using dual supplies, direct coupling of the source possible at the input. Then we have Rd as the resistance to be fixing the VDG, and let us say we have possibly an RL coupled to Rd through a coupling capacitor Cc, and Rs to fix the IDSQ at 1 milliampere in a stable manner, and that is bypassed by Cs. So, for 1 milliampere operating current IDSQ, the VGSQ needed, VGSQ is equal to, we know, root of IDSQ by K plus Vt. This is from that relationship IDSQ is equal to K into VGSQ minus Vt whole square. So, from that we know VGSQ is equal to 1 by 1, that is 2, 1 plus 1, that is 2 volts. This we had earlier also evaluated. So, VGSQ is equal to 2 volts. Now, we have this fixed at 2 volts. As I told you, I know that the operating current is 1 milliampere. I want this 2 volts to become negligible compared to the drop across RS. That is what is meant by stable way of biasing. So, that means I should have the drop of the order of 10 times 2 volts, which is 20 volts. So, I am now therefore making the operating point very stable. Operating point becomes relatively independent of the field effect transistor. Right. So, if this is 2 volts, I am selecting to make the operating point independent of the FET characteristics this drop as 20 volts. So, if this drop is chosen as 20 volts, so IDSQ into RS is chosen as 20 volts. Okay. Why is it chosen as 20 volts? Which is much greater than this VGSQ. That is the idea. Okay. So, RS therefore becomes equal to 20K because IDSQ is 1 milliampere. So, RS is now fixed at 20K. If RS is 20K and this is 20 volts, VESS is automatically fixed at 20 plus 2 volts, that is 22 volts. So, this is 22 volts. Okay. If it is dual supply, if this is minus 22 volts, I would definitely have VDD also as plus 22 volts. And if this is 10 volts, that is what the swing should be, output swing, corresponds very nearly to VGDQ in one direction, right. So, if this is 10 volts, is this clear? On one side before it goes to triode region, right. So, this is very nearly equal to 10 volts. Actually, we know that this can now go to minus plus 1 volt. So, there is a swing possibility of 11 volts on this side. So, anyway, I am fixing this as 10 volts. Then this drop is going to be how much? 22 minus 10 volts, which is 12 volts. So, if this is 12 volts, RD is going to be equal to 12K because IDSQ is 1 milliampere. If RD is 12K, RD is equal to 22 minus VDGQ divided by 1 milliampere. This is equal to 12K. This being chosen as 10 volts. That is because of the swing possibility. Now, this is 12K, RD is 12K, and therefore, other swing is IDSQ plus delta IDS. That delta IDS can become equal to 1 milliampere now. So, IDSQ into 12K parallel RL is the other swing possible. If current swing possible is IDSQ, right, then the voltage swing because of IDSQ swing of current is equal to 12K parallel RL, which is 12K into RL divided by 12 plus RL, and that should be equal to how much? 10 volts, because we want symmetric swing. So, this will give RL as how much? Please find out. 120 10 RL, okay, that is, this is 1 milliampere, 60 K. That will be 72, 12 into 60, that is all right, right. So, RL is 60 K. So, this completes the design as required. What is it? It is going to definitely give you a symmetric swing of about 10 volts, okay, on either side of the quiescent. Now, this under the assumption that this side it can go up to 0 volts, but it can actually go up to 1 volt. That means, on one side there is a swing of 1 volt extra given. That is because we do not know that there is going to be some swing here, it is not going to remain constant. When this goes down, this will go up. Okay. So, definitely we are going to give some amount of leeway for this voltage to increase here, okay, so that it will definitely be less than 11 volts. Is this clear? So, it is not going to be full 10 volts, okay, it is going to be strictly speaking 11 volts on one side, but since this voltage is going to increase, it will reduce the swing. So, once this design is over, we can now go to evaluating the performance of the amplifier. So, we will put down the equivalent circuit now as 100K Vs coming to gate, and then we have Gm into this VGS, this is VGS, and RDS, RDS is not given, so we will take it as infinity, and then RD, which is 12K shunted by 60K, which is the effective resistance, right. So, this is the equivalent circuit of our amplifier there simply. Now, what is the value of Gm? Gm at the operating point is 2K into VGSQ minus VT. So, this is equal to 2, K is equal to 1, VGSQ is equal to 2, this is equal to 1. So, this is actually equal to 2 millisiemens as before. Right. So, we have here this kind of output. So, what will be the output voltage here? Okay, V naught, 12K parallel 60K, which is anyway known to us, that was 10K. We wanted to make it equal to 10K earlier, right. That is how we selected the value of RL. Okay. So, this effective combination is 10K. So, gain, voltage gain, again minus, because this becomes plus and that becomes minus actually, minus Gm, okay, into 10K, which is minus 20. This is a good amplifier, right. Gain is fairly high compared to what we got yesterday, which was minus 4. Okay. So, this amplifier has a fairly high gain, in which case I could really consider that this voltage is very small, and therefore, VDG swing is the same as, okay, V naught. Otherwise, VDG is going to be evaluated, okay, from the fact that there is a voltage going down here, there is a voltage going up here. So, it will be reduced, okay, and therefore, this particular thing is so small compared to output swing that we can now neglect this variation. Consider that this is very nearly at ground potential in this case. Is this understood? So, we have the voltage gain. Next, we have to determine the coupling capacitors and bypass capacitors. Now, we will say that the minimum frequency of interest is equal to 100 hertz. So, the capacitor should be short circuits compared to the impedance resistance coming across the capacitors, okay, at the minimum frequency of interest. Short circuit means we will make the reactance of the capacitor equal to 1/10 the resistance seen from across the capacitor. Okay. So, this is the guideline for designing it for a specific minimum frequency up to which it has to function satisfactorily. Now, let us consider the coupling capacitor Cc. The reactance of the coupling capacitor 1/2 pi F minimum into Cc should be much less than, what is the impedance seen from there? That is very clear. Cc comes here. So, this is current source. We have 12K in series with 60 kilo ohms. So, 72 kilo ohms. Now, there are two things. If you want this to be a short circuit, then 1/2 pi F minimum into Cc is taken to be equal to 7.2 kilo ohms. But if you want Cc to fix up the lower cutoff frequency, what is the lower cutoff frequency? It is the frequency at which the gain falls to 1/√2 times, okay, the higher frequency gain. Okay. At that frequency, what happens is the reactance of the capacitor will become the same as that of the resistance seen. Okay. So, you will simply equate, if you want Cc to fix up the lower cutoff frequency, you will simply equate this reactance to 72 kilo ohms. Okay. If you do not want it to fix the lower cutoff frequency, then you want it as a to act as a short circuit, then this will be chosen as 7.2 kilo ohms. So, Cc can be now evaluated, okay, accordingly. So, that is equal to 1/2 pi, okay, F minimum is 100, okay, into 7,200. Okay. How much is this? This is about 221 nanofarads or 0.2 to 1 microfarads, which these capacitors are readily available to us. So, you can now see how the coupling capacitor is fixed. Okay. Next, we will consider how to fix the bypass capacitor Cs. This is an important aspect of design. Once again, it is now assumed that this is a short circuit. This is important. Okay. So, that means this is going to be 10K. So, we will put down this. Apart from that, now this is not, we have this, okay, which is 20K as the source to ground resistance, and therefore, now we have to apply a voltage here, source V0, then remove this because this has no place, short circuit all other independent voltage sources, apply a voltage V0, and find out the current I naught. And V naught by I naught is the impedance, right, seen across RS, okay, CS. Okay, therefore, let us call it R naught. So, this CS should be such that 1 over 2 pi f CS with minimum frequency of interest should be much less than what? This impedance R naught, if you want it to function satisfactorily up to f minimum. But if you want this f minimum frequency to act as the lower cutoff frequency, then you will equate this to R naught. Okay. So, otherwise you will make this thing 1/10 of this reactance, 1/10 of R naught. Now, let us find out how we can determine R naught. Once again, this is an important aspect of design. Here, please look at the circuit in this case, right. This 10K is connected, okay, one end of 10K is connected to this ground. So, this is not correct. Okay. RDS is equal to infinity. So, no RDS. So, now if this is V naught and I naught is what we have to find out, this voltage, this current is V naught by 20K. This is simple, right? And this is V naught, this is V naught, and VGS is minus V naught. So, this becomes VGS becomes minus V naught. So, this is a minus GM V naught current source in this direction, or plus GM into V naught in the opposite direction. So, I will make this plus and change the direction of the arrow this way. So, you can see that there is a current dependent upon V naught flowing in this direction as well. That means, this can be replaced by a resistance of magnitude 1 over GM, because current voltage across this is V naught and the current flowing in out of this, okay, is GM into V naught. So, the resistance seen from here like this is voltage across this is V naught and the resistance is 20K. So, the current is V naught by 20K. So, the total current I naught is equal to V naught by 20K plus GM into V naught, or I naught by V naught is equal to 1 over 20K plus GM. This is an important relationship. What it simply says is that when I look at it from source to ground in a circuit of this type, always the impedance seen is impedance across it, which is 20K shunted by 1 over GM. 20K shunted by 1 over GM. In this example, GM is 2 millisiemens. So, which is, this is 2 millisiemens or 1 over, okay, 0.5 K. So, it is equivalent to 0.5 K here shunted by 20 K. So, essentially it is going to give you V naught by I naught, which is equal to, very nearly equal to 0.5 K. That means, this is essentially equal to 0.5 K. That means, if I want this to act as a short circuit, CS is going to be chosen such that 1 over 2 pi CS into F minimum is equal to 50 ohms, 1/10 that. So, Cs therefore is equal to 1 over 2 pi into 100 into 50. This is again 100, that is equal to about 31.8 microfarads. So, the next topic of interest for us, now that we are aware of how to design a basic amplifier configuration, whether it is common emitter or common source, it does not really matter. We know how to design it for a swing or for a particular gain, etc., and how to evaluate its input impedance, output impedance, okay, etc., and also how to estimate the lower cutoff frequency and upper cutoff frequency, etc. Now, we should also learn about an important aspect of design in case our amplifier gain by a single stage is not sufficient, how to improve it by what is called as cascading amplifiers. This is what is done in order to improve the gain over and above what a single stage can give. So, cascading means we have basically a source and a first stage amplifier this is normally called pre-amplifier. In fact, we worry about all these aspects simply because designing a pre-amplifier is different from designing other amplifiers. This has lot of responsibilities. Okay. This is what is called the front end amplifier. Okay. It is facing signal in some form or other. Okay. We do not know how it is facing the signal. It may be that the antenna signal comes here, okay, or a transducer signal comes here. Okay. So, it is going to face a variety of input voltages ranging from some value to some other value, okay, and output impedances, source impedances. Okay. So, this characteristic of this drive might keep changing, right, from time to time. So, this pre-amplifier is an important thing. It is required to normally act on very small signal level, and therefore, it need not really operate at what? Large currents. Now, operating point is basically going to determine the output swing that we have already established. If I have an operating current of 1 milliampere, I can have a swing of 1 milliampere. If I have an output operating current of 2 milliamperes, I can have a swing of 2 milliamperes. Now, when you are required to have only a current swing of let us say 0.01 milliampere, as might be required in the case of a pre-amplifier, why should you operate it at 1 milliampere? You might say, why not? Obviously, when the signal is not coming, it is still continuing to take that 1 milliampere current from your battery and will dissipate the battery, loss of power unnecessarily. Okay. This is what happens when even the signal is absent. So, this kind of thing should be avoided. So, when the signal is present, anyway it is required to amplify, therefore, it has to operate at a certain current, right. So, basically the pre-amplifier operating current has to be chosen as small as possible. For that matter, any amplifier operating current should be chosen as small as possible, because even when it is not amplifying, it is drawing that much amount of current from the battery. Okay. So, this is an important aspect of design, in which case these amplifiers operate at low currents. And next, the responsibility of this is not so much as the responsibility of pre-amplifier, because this is facing the same species, okay, an amplifier here, okay, is what it is facing as is input. Already certain things are automatically fixed for this. So, this is maybe a second stage. So on, you might have to cascade so many amplifiers, right? Now, what is the effect of cascading? Okay. If we know that this amplifier is non-ideal. Once we know that this is non-ideal, what do we mean by that? We know that it has a finite input impedance, finite output impedance, okay, and of course gain. So, it has its input impedance, it has its output impedance, and it has its voltage gain or current gain, whatever it is. So, we will consider here this is VI1 and therefore, it is AV times VI1 is the voltage gain, let us say. For example, for the example that we had just now worked out, AV came out to be 20, right. So, in this case AV came out to be minus 20 because it was an inverting type of this thing. So, I have now used a non-inverting amplifier, right. So, 20 and input impedance was infinity, okay. Output impedance was equal to I think 12K, right. So, 12K, okay, was the output impedance and that was shunted by 60K, okay, which was considered as the load. Now, for this the load is going to be the input impedance of the next stage. So, R in 2. So, this is important. Input impedance of the next stage is going to be the load for this. And again we have output impedance of that R out 2 and AV1 we will call it, AV2 and VI2. The VI2 is this. So on. So, what happens now due to cascading? We can see here that the gain is reduced compared to open circuit gain. Gain is reduced by a factor of R in 2 divided by R in 2 plus R out 1. Okay. So, R in 2 by R in 2 plus R out 1 is the gain reduction factor here. Okay. And therefore, if you now have requirement of finding out the overall gain, right, it will be from here AV1 into R in 2 by R in 2 plus R out 1, okay, into AV2 into R in 3 by R in 3 plus R out 2, so on. So, you can therefore see that while cascading we will get all these gains as multiplication factors, but all these gains will be reduced by a factor of, okay, the next stage input impedance by next stage input impedance plus the stage output impedance, so on. Is this clear? And coupling, we can keep on doing this, R in 3 by R in 3 plus R out 2, okay, so on it will be. Now, what about coupling? Obviously, one stage can be coupled with the other stage using capacitive coupling or direct coupling. So, it could be capacitive or direct coupling. Obviously, this capacitive coupling has this advantage that one operating point of one and the next one can be independently chosen, and this capacitor will isolate the DCs. Now, if it is direct coupling, let us illustrate this by taking an example. This is the first stage. Let us say it is VCC, RC. I am taking a bipolar stage. I have bypassed this, right. Now, I can couple this on to another stage. Okay. The next stage is also a common emitter, let us say. This common emitter is using dual supplies, so I can directly couple my signal onto this. So, I do not have to worry about capacitive coupling here, I can directly couple the source here, just as we did in the last example, okay, of common source amplifier. This is a common emitter amplifier. So, how do I do it in the next situation? I have to put a resistance here, right, so that this voltage is coupled onto the base of this, and then it will have its RE2, let us call this RE1, this will RC1, okay, and so this is how I can couple. Is this clear? This capacitor CC can couple this output directly to the base. Why is this resistance needed? This resistance is needed because there is a DC base current which has to pass through. Okay? So, this resistance is a must, we cannot avoid this resistance, right? And the AC coupling is done by the capacitor. So, this we will call it as RB. How do you select RB? RB, okay, divided by beta plus 1 should still be small compared to RE2. This I have told you earlier. Okay. RB divided by beta plus 1 should still be, okay, less than RE2 for stable operating point, so that this drop across RB can be neglected as far as the DC is concerned. Okay. So, this is how the capacitive coupling can be done. Now, obviously, this is also common emitter. So, we will put it CE1 and this is CE2, bypass capacitor. You can see that the order of CE1 and CE2 will be of the order of tens of microfarads that we had seen in the example, maybe even hundreds of microfarads. Okay. CC of course will be of the order of microfarads. Okay. So, these are all huge capacitors, and in this day of micro miniaturization, right, when all these other circuits including these active elements, transistors and resistors are becoming smaller and smaller, these capacitors of the order of microfarad still remain to be very big in size. So, if it is a micro miniaturized circuit I am planning, there is no place for these capacitors. That means what do we do? There is no other way other than, okay, take recourse to direct coupling. So, this is avoided, okay, simply because large valued capacitors cannot be fabricated by present day technology of monolithic ICs. Right. So, these capacitors are not available. I cannot make an IC out of it, okay, if you say that these capacitors must be used. If you say that it must be used, it should be put externally. If it is to be put externally, imagine the number of terminals I have to bring out. Okay. So, just for an amplifier I might have to bring out several terminals. Okay. So, this is avoided by simply direct coupling. Okay. We will come to this later. So, coupling is made direct. Obviously, if you can do direct coupling, it avoids large valued capacitors being used for coupling and saves a lot in terms of area, okay, and the circuit can become a monolithic IC, micro miniaturized circuit without any problem. Now, what are the disadvantages? This is important. Suppose I go to direct coupling, what do I lose in terms of flexibility in design? Now, we have just now seen that the swing of the stage, symmetric swing, output swing, depends upon the operating point. What are the two factors that determine the swing? Operating current and, in this case, operating current and collector base voltage, VCBQ and IC. One swing is determined by VCBQ. Okay. If VCBQ is 10 volts, it can swing up to 10 volts, right? And operating current, if it is 1 milliampere, it can swing by 1 milliampere. So, these two are important factors which determine the swing. Now, consider here, there must be some VCBQ. Of course, this VCBQ at the pre-amplifier stage could be made very small, because if I am designing for certain volts swing, let us say 10 volt swing, and the amplifier gain is 1000, if I am designing for 10 volts output swing finally, and the amplifier gain is 1000, and 1000 is not got by one amplifier, let us say it is split between several amplifiers, okay, first stage, second stage, third stage, something like that. First stage gives let us say gain of 10, second stage gives gain of 100, third stage gives gain of 1, something like that. Okay. So, if it is distributed like that, then obviously the first stage is handling a signal of only how much? 10 volts by 100. Okay. So, output stage is handling 10 volts. Okay. So, this output of the first stage is handling only 10 volts by 100. Okay. So, this is an important aspect. That means, the swing, voltage swing needed for the pre-amplifier is normally extremely small. So, you do not have to provide, actually speaking, any VCB at all, or even if you provide it, if you provide a voltage of the order of few volts or hundreds of millivolts, that is sufficient. Okay. Same is the case with current swing. If the final stage has to have a current swing of 20 milliamperes, okay, and you are having large number of stages, the first stage might have to handle a signal current swing of only few microamperes. Okay. And therefore, the operating current of the first stage need to be of the order of few tens of microamperes. So, you do not have to select this operating current to be very large. So, these are the things. But while now direct coupling, what happens? This has some voltage, okay, because of its swing we have provided. The next one will have more swing. So, the next voltage, the quiescent voltage has to be higher. Let us say we provide 1 volt here, we provide 10 volts here. Suppose the third stage is coming, it will be still higher. What is happening now? This voltage is fixed, right? So I am actually getting lesser and less swing possible for the output stages because of direct coupling. Okay? So this is the disadvantage of the direct coupling. As the gain keeps on increasing, this voltage has to be progressively higher and higher for obtaining higher and higher swings, but that is going to reduce the swing available at the output. Okay. Now this can be tackled obviously by using, if this is NPN, the next stage I use, if it is made equal to not this, I use what? PNP. No problem. So this has gone higher, okay? Because this has gone higher, right? This swing here is going to be still higher, okay? So you can now see therefore that by using NPN and PNP we can get rid of this problem of swing limitation, okay, for higher stages, later stages, okay, by using what is this? This kind of complementary, okay, transistors. We can avoid this because next again you will use what? NPN. So again this has got enough swing. Let us say you provide enough swing here, so this has gone down further. That means again the collector to base potential can be kept pretty high for each one of these stages. Is this point understood? Okay. This is one way to avoid, okay, being limited to small swings at the output by using NPN and PNP stages. But in some technologies you do not have both types of transistors equally good available for you. Suppose you have to design amplifiers using only NPN. Then what is the problem? The problem is how to reduce this voltage. We can reduce this voltage by what? Potential divider, right. Something like this. Okay? Reduce the DC voltage here. This has gone high, reduce it and then apply. But what happens? This will also reduce the gain. Because this whatever DC voltage undergoes, the AC voltage also undergoes, right? The signal voltage. So this is not a good scheme. You should not affect the AC. You should only affect the DC. That means, okay, we can introduce a current source here because this is the one responsible for attenuating. So I put a resistance and a current source. So this kind of again this is going to drop it by, if this is R, okay, this is going to drop it by I naught into R. You can reduce it. These are called level shifting circuits. This kind of putting a resistance also is not very good, okay, because even if you let us say put a current source, there is going to be input impedance of the next stage, and if you put a resistance, again AC is going to be attenuated. So you have to put instead of a resistance a battery, right, and that kind of battery is available in circuits as Zener diode. Okay. So Zener diode will drop a DC. As far as AC is concerned, it is very nearly a short circuit. Okay. So this kind of thing requires the need of something like a Zener diode and a current source. So we will discuss in the next class how to obtain these current sources. We will discuss also later how to get rid of the bypass capacitors, because we have got rid of the coupling capacitors. How to get rid of these bypass capacitors also will be discussed in the next class. Then how to generate this current